So this is a conservation of energy lecture, and we're going to talk about some examples here, and also talk about how how we deal with thermal energy, and when that shows up in our conservation of energy equation, and whether we call it delta U internal or delta E thermal. We'll talk about that. So this first example here, we have an acorn dropping from a tree. It says calculate the final velocity of the acorn with the acorn alone as the system. So if the acorn alone is the system, then we can go ahead and draw, I like to draw a dotted line around the system. Here I'm using a bright yellow color. Hopefully that's visible and not too hard to see. This means that when the acorn alone is the system, that the force on the acorn, which we know as the force of gravity, is an external force. We're assuming that, I'll go ahead and write that down. We're assuming that that the acorn's already left the tree. So there's no, the Earth is not in the system. If the Earth is part of the system, then gravity is internal. So we are considering the Earth outside the system, so therefore force gravity is external. This means that gravity is going to do work, and external forces do work, internal forces do no work. We saw in the last unit that external forces change the momentum, right? Cause impulses. External torques change the angular momentum. Here we're saying external forces do work and internal forces don't do work on the system. Work is a change in energy. All right, so I'm going to go ahead and write the conservation of energy formula. EI is equal to EF. And it doesn't matter which way you write it. Sometimes you see this written as MEI equals MEF or MEI equals MEF. You see that? That just means mechanical energy. Mechanical energy is kinetic and potential energy. So that's another way it can be written too. Okay, so we said last time that work always goes on the initial side. So we'll go ahead and put that there. It's the work done by gravity. On the final side, right before the acorn hits the person in the head, right? I think that's what happens here. Yeah, it looks like somebody's gonna get hit in the head by an acorn. Is gonna be just kinetic energy. So we're calling this position right here. Notice where the person's head is, the top of the person's head. We're calling that 0 meters. So that's important right there. Okay, so we're saying that the acorn starts at yi, which is 20 meters, and then is going to fall 20 meters, right, to 0 meters. And this is the distance it's going to travel. Yeah, so we're not calling the ground 0. And we can do that. We can call any point 0. That's fine. All right, so we have the work done by gravity here. That's going to equal FD cosine theta, right, just like before. KEF is going to equal 1/2 mVF squared. And I'm going to be a little more specific on the other side too, right? So we can say that F is really, well, I guess I might as well just write it in here, right? Is equal to FG. And so it's FG times the distance times the cosine of theta. Let me get rid of this. Okay, so what is theta? Well, if we go back up and look, here's FG, right? We can just draw a distance in. Let me use a red marker for distance. So this is going to be D. It's equal to 20 meters. So what's the angle there between those two vectors? We would say, well, it's obviously there's no angle there because they overlap. So we're going to say theta is equal to 0 degrees. All right, so we'll come back down here, plug that in the equation. So we're saying FG is MG. D is equal to, we just said 20 meters. And we have the cosine of 0 degrees. Cosine of 0 is just 1. You know, just plug it in your calculator if you want to check. And we have that equal to 1/2 mVF squared. And only the VF gets squared. All right, so let's go ahead and do some canceling here, right? We got an M on each side. We can get rid of that. I think that's about it. All right, I guess I could have left that as, instead of G 20 meters, I could have left it as GD. Why don't we do that right now, right? Yeah, let's leave it as let's leave it as D right now. And then we'll come back and put the 20 in later. I kind of like to solve in terms of variables just to see what happens. So we have G times D is equal to 1/2 VF squared. Multiply both sides by 2. 2GD is equal to VF squared. So we can, instead of writing the square, we can just square root both sides. So we're saying that VF is equal to square root of 2GD, right? Now, if we plug the numbers in, we can actually solve for an amount here. So we have the square root of 2 times 9.81. Remember, G is not inherently negative. We make it negative in certain problems, projectile problems, for instance. And we do that by adding a negative sign. But in this problem, remember what we said about work. We don't let the force, we don't give it a sign. We use its magnitude. So here you would not tack a negative sign on, right? Let the cosine theta determine the negative sign. And here it's telling us it's a positive 1, so there's no negative sign. All right, so coming back down here, D is distance, which is 20 meters. All right, so we do the math there. I think we end up getting 19.809. Meters per second. And here's where we run into a problem, right? If down is negative, which let's say it is, right? Go ahead and write that up here. It doesn't change anything, right? We still solve the same way we did. It doesn't make, remember we use the magnitude. Even though force gravity is negative, we use the magnitude, so it doesn't change a single thing. So you might say, well, the velocity here at the end, right, when you square root something, has to be negative, right, because the acorn's falling down. So what my point is, when you square root something, you have to pick from the positive or negative value, right? Because negative 19.809 squared is, or when we do a square root, we get a positive or negative answer. It's kind of it's kind of what I'm trying to say here. So yeah, so you have to go ahead and pick the correct one for the problem, which is the negative one. Okay, good. Yeah, I was going to say negative 19.809 squared is equal to 2GD, and positive 19.809 squared is equal to 2GD. So you have to pick the correct one. Okay, let's go to the next problem here. So I think the next problem says we're going to do the exact same thing, but now we're going to consider the system to be the acorn plus the earth. So what we have then, let's do another drawing here. So we have the earth down here. We have the person. Not a very good drawing. We have the we have the tree. Pretty rough looking tree. Okay, and then the acorn. Okay, so this acorn is going to fall once again and travel a distance of 20 meters. We can call this yi. It's equal to 20. Call this yf. It's equal to 0. It's meters. This person's face, I guess it's okay. So, all right, that'll work. I thought it looked like the person had 3 eyes, but I guess that's the nose. I don't know. Anyways, okay, so now our system, let's go ahead and write that in. Let's use that yellow marker. Our system is going to be the acorn plus the earth. So it's going to be this. And dotted line the word earth into it. Okay. And this acorn is going to hit the person in the head. It's not drawn perfectly correctly, but you get the idea. I'm not sure why I didn't include the person in there. It doesn't really matter. The person doesn't change anything, so I guess I can do that over. Oh, dang. Now I'm just erasing everything. All right. Let's just leave it because I don't want to erase everything. I could have just drawn a perfect rectangle there. It would have been fine. Okay. So if this is the case, then we can go ahead and do our energy balance. Same as before. But now, gravity is an internal force, and that's kind of what I wanted you to see. So what's going to happen here is when gravity is internal, that changes things. Another symbol for potential energy is just the capital letter U. So this is kind of the important idea here, is that when gravity is an internal force, there is potential energy, gravity. And so what I'm saying is you either have gravity being external and doing work, or you have gravity contributing potential energy. It's one or the other. You cannot double dip. Gravity can't do both. It's one or the other. All right. So do not have gravity doing work and have potential energy gravity. Now it makes sense if you were sitting there a second ago saying, well, the acorn's starting up in the air, and when something's high up in the air, it has potential energy. And Mr. Rodriguez just completely ignored it right here. And I just forgot to mention it because I was looking at my notes. But I can write that down, right? I can write that in right here. So when gravity does work, right? This is when it's external, right? I'll just write that down. It is external. There is no potential energy grav. All right. And the idea, once again, is you cannot double dip. You can't have it doing both. All right. So here we had no PE gravity in this energy conservation. And here we are going to have gravity be internal. And then therefore it's not doing any work, but we do have potential energy initial for gravity. We don't have any potential energy final when the acorn hits the person in the head. Why is that? Well, because the height would be 0, right? We said that this line right here is 0 meters. And so therefore PE is equal to mgh, and you don't have any potential energy there. Because I could see a student being confused and being like, well, the acorn can still fall further, so where's the potential energy? Well, we're calling that point 0, so therefore there's no potential energy at that point. All right, so coming over here to this then, our conservation of energy formula simplifies into PE initial is equal to KE final. And this is right before the person gets hit in the head is the final. So we can then write our formulas. PE is equal to mgh initial, and KE is equal to 1/2 mvf squared. We can see once again that we cancel off the two m's. I'm going to leave variables kind of the way they are, and not put numbers in, right? Multiply both sides by 2. We get 2g h initial is equal to vf squared, square root both sides. Vf is equal to the square root of 2g h. And you can put h initial or you can just put h, whatever, it doesn't matter. And that is the exact identical thing. Whoops, I was trying to do the highlighter. That was exactly identical to what we had a second ago, right? And then we solved for VF, right? We called it 2GD, but D is the same as H, right? They're both 20 meters, so it all works out. It's all good. Okay, good. Let's look at the next problem here. So one thing I want to point out before we move on, the system, the problem doesn't, the acorn doesn't care what you call the system. Why is this not writing? Hold on, I think I fixed the stylus. Sometimes the tip of it unscrews and then it doesn't write. The acorn doesn't care what you call the system. So the system is a mental construct. It is something that changes how you solve the problem, when it's defined differently, right? But it does not change the problem. And that's important because the system is it's a tough idea to understand, right? It's abstract. It can be picked differently. And so if you're not quite grasping it or understanding it, I see why, okay? But with some practice, it should make sense. So once again, the acorn doesn't care. Acorn's going to do what it's going to do. It's going to get the speed or the velocity that it's going to get at the end. It doesn't care what you call the system, but it will change how you solve the problem. Okay. The next part here. A box is pulled across a rough carpet at a very slow, constant velocity. So here we have, initially the box is moving at some velocity and across this carpet. And then this is like a before. And then in the after, the person's still moving the box at the same velocity, but has traveled some distance d. Okay. So a box is pulled across a very rough carpet at a very slow constant speed. If the box alone is the system, analyze the two balanced external forces. Okay, I might get a separate sheet of paper here because this is getting kind of rough here. So let me put a piece of paper in here. Okay, so once again, that question was, if the box alone is the system, Analyze the two external forces. All right, so, okay, so this person is pulling on the box with the rope. Okay, something like that. And let's draw a dot on the box, because we like to draw our forces coming from that. The carpet is rough. Rough is code for friction. When you see that rough surface, it just means friction. So that's the person that wrote the problem talking to you and telling you that. You have tension from the rope. Remember, tension always pulls, never pushes. So it's going to point that way, which is the way the box is being pulled. This is all about the box. When we do a free body diagram, all the forces we draw are all about one object, and that is the box, and they all emanate from the center. Okay, we have friction, which opposes motion, right? And this is going to be force, friction, kinetic. Now, these are the only two x forces. Now, we know that there is a velocity that is constant. So if the velocity is constant, what do we know about the magnitudes of these two forces? Well, then we know that there is no net force. We know that F net is equal to 0. So what I'm trying to say is we would know that the sum of the forces in the x direction is equal to 0. So if say right is positive and left is negative, we know, this is a sigma, kind of doesn't look like one. We know that we would just write tension, right? Because it's a positive force, so I put a positive sign on it. Friction is a negative force, so I put a negative sign on it. And we know that this is equal to 0. So we know the magnitudes of the two are equal. Their directions aren't, but their magnitudes are. So if tension is 10 newtons, friction kinetic would be negative 10 newtons, right? Or, yeah. And so I would just plug the magnitudes in here. I would plug 10 in for T and 10 in for force, friction, kinetic. I wouldn't put negative 10 in for force, friction, kinetic because I already have the negative sign right there. So you don't write the negative sign twice. All right. I know that's confusing too sometimes. Okay. So let's go back up to that question, or down to the question. If the box alone is the system, analyze the two balanced external forces. So they are balanced. They are both external, and then it says, I don't know what I was trying to go for, but I'll just write that their magnitudes are equal. Okay. What is the work of the rope on the box? Okay, so I think we can write this, right? We know our work formula is W equals FD cosine theta. With the rope, we have work being, I'm not going to write W because I'll just go for, the force is going to be tension, right, from the rope. The distance is going to be, I think we just called it D. And then we have the cosine of what angle? Well, we said that the box is going to travel this distance right here, which is D. I kind of like drawing that there. I kind of want to, though, let me see. I kind of want to draw D as a vector. I almost hate doing this because it's not a force, and where I'm drawing it kind of ticks me off because I don't want you to think it's a force. It's not a force. But if we think about this like a work problem, we can now see what is the angle for what is theta for tension. We can see that it's equal to 0. What is theta for force friction kinetic? Well, we can see now that theta is equal to 180. About to write a negative sign, jeez. Is equal to 180 degrees. So that right there is going to allow us to write these work formulas, right? They're both forces are going to act over a distance d, but we're going to see that tension will be positive because cosine 0 is 1, and friction kinetic will be negative because cosine 180 is negative 1. All right, so coming down here then, we can see that this is going to be, switch back to black here, this is going to be cosine of 0, so we get the work of the rope on the box, we get W of the rope is equal to TD, right? And because cosine of 0 is just 1. And down here, what is the work of friction from the carpet? We can say, well, it's the force friction kinetic times D times the cosine of 180, which is equal, cos 180 is negative 1. So we can say the work done by friction is equal to force friction kinetic times D negative force friction kinetic times D. I don't know if that negative sign's easy to see. Let me make it red maybe. All right, I don't know if that helped. Okay, so you get the idea, right? Work done by the rope is TD. Work done by force friction is negative friction kinetic times D. Okay, then are these forces equal and opposite? Yeah, right? The answer here is yes. We said that, right? To travel at a constant speed, these forces would have to be equal and opposite. So their magnitudes are equal. The reason that's important is that if their magnitudes are equal, we can see then that if work done by the rope is maybe 10 times the distance, 10 for tension, maybe it's 10 newtons, then for work done by friction would be negative 10 newtons times the distance. So these work amounts are going to cancel. So when we write, let me go ahead and write yes. Okay, so let's write the conservation of energy below. And I think I'm going to add a page here just because I like a little more room to write here. Okay, let's get rid of that. So we're saying, let's go ahead and write EI equals EF. Remember, work goes on the initial side, and initially the box was moving. So we're going to have kinetic energy initial. We have two types of work. We have the work done by the rope, which is positive, and then we have the work done by tension, or by friction, which is going to be negative, right? So we're going to add in the work done by friction. I know that's going to be negative, but we'll let the cos 180 deal with the negative sign. So we're just adding the types of work and types of energy initial. Final energy, we have KEF. The box is still moving. And we don't have any other types of energy, right? There's no springs involved. There's no potential energy of a spring. There's no potential energy gravity because there's no distance for it to fall or to move in the y direction, right? So there's no height. All right. So anyways, coming back to this, check this out, right? What we're proving here then is if the work, let me go ahead and write these out here. So we're saying call that TD. We'll call this net minus force friction kinetic times D. And and KEI and KEF are actually equal, right? But anyways, what we can see is these cancel, right? That TD, because force friction by magnitude is equal to T, right? This is like almost saying TD minus TD, right? So these are going to, well, I don't need to make it an arrow. Let me erase that. I'm just going to cancel them off. Okay, so we end up proving that energy is conserved and KEI is equal to KEF. And everything is good. Life's good. It works out. And energy is conserved. The universe is happy. All right. So the problem, though, the reason we aren't happy is because the box heats up. And this makes us unhappy because we don't have a way to explain this, right? It's not in our formula, and that's a problem. So, how do we deal with it, right? Let's go ahead and go to the next page. Well, it's similar to what we saw before, where if we have potential energy gravity, then gravity doesn't do work. Well, this is very similar, but we're going to have a different kind of energy. We're going to have a change in heat energy, and that we're not going to be able to specifically know how it's shared among surfaces, right? Because if we go back and look at this, it's not only the box that heated up, right? The surface did, right? The carpet did. And so both surfaces heated up, and so we have to explain this energy. We know it's we know there's energy there. We can even specify the amount, but we have a hard time saying exactly where that energy is. If it's in the box or if it's in the carpeting, yeah, it's tough. So let's redraw it. Oh yeah, that was a good smiley face that time. All right. This time, I think last time did we say that the box itself was the system? Well, I'm saying it now. I don't know why I didn't say it last time. So last time the box itself, just the box, was the system. And I want to make a note of that. That's kind of hard to see that yellow. Let me put a little black in there and maybe that'll make it easier to see. So last time, system was box only. And this time, the system is going to be, I guess I could just draw it here, couldn't I? No, it's just so far away. I'm going to do it right back here where I was. This time, the system is going to be the box plus the floor or the carpet. And you can probably already guess what this is going to do, right? So I'm saying the system, I'm going to try to not include the person. And the reason why I'm doing that is because the rope is going to stay external. The rope is an external force. So let me put a little black in there so you can see my yellow highlighting better. I don't know if that helps, but it doesn't hurt. All right, so the system equals box plus carpet. All right, so what this means is that force friction, which I think we drew as purple, is an internal force. Just write it right up here. and therefore does no work. All right. So that means that this energy is going to be showing up somewhere else, and that's going to be in the heat. So, once again, this is similar to gravity, right? Either doing work or being potential energy gravity. Here we have friction, either being external and doing work or being an internal force, which we're going to represent as delta E thermal or delta U internal. And just some kind of change in heat energy that is going on, and it's always going to be drawn on the final side. So here we have let me finish drawing this. We have tension as an external force, and these are, I should really be more careful there because these are a Newton's, well, they're not a Newton's third law pair, but they're equal and opposite. So I should draw tension pointed at the same size, right? The same magnitude. Okay, so what we're saying here then is let's say this. Let's remind ourselves what the work done by the rope is. The work done by the rope is equal to tension times distance times the cosine of 0. But we said a second ago, right, that in terms of magnitudes, tension, let me write this. Let me write this up here. Tension is equal to force, friction, kinetic. I'll just write equal magnitudes. So that's what I'm saying here, just for magnitudes. Okay, so what I can do then is I can rewrite this as force, friction, kinetic times the distance. And because cosine of 0 is just 1. And what we did right there is derive another way to express the work done by the rope, right? And the reason this is important is because this work done by the rope is going to be in the final part of our conservation of energy, showing up as that delta E thermal, as the heat, right? So we're going to call it either delta U internal, or, which means potential energy internal, right? So INT means internal, which I guess would be internal to the system, right? It's shared between the carpet and the box, but we don't know where it is in the system. All right. Or we call it delta E thermal. And thermal just meaning heat, right? Okay. So you can use either symbol you want. I think the Knight textbook uses this one, and the Akina textbook, which I also like, uses this one. And it doesn't matter which you use. But when we write these on the final side, delta U internal or delta E thermal, what we're going to write for what they equal is this right here. And what this whole example problem, the point of it is to prove where this force, friction times distance comes from. Because I could have just given you these formulas, but you would have been like, well, where the heck did force, friction times distance come from? So what it comes from is that it is another way of writing the external work being done on the system And but you could even think of it instead, right? But that's more related to this problem. But you can think of it instead as this, right? That it is the way friction is expressed when it is an internal force. When friction is external, it does work. When friction is internal, you have delta U or delta U internal or delta E thermal. So once again, force friction kinetic is external. Then that means that force friction kinetic does work. If force friction kinetic, once again, you can't double dip, right? They can't do, force friction can't do both, is internal, then delta U internal exists on the final side of the conservation of energy. Okay, so this is very similar to what happened to gravity and how PE does or doesn't exist. PE grav, right? Is gravity doing work or not? And is gravity internal or external? Okay. All right. Almost done here. One more example. You're driving your car when another car crosses the road at an intersection in front of you. To avoid the collision, you apply the brakes, leaving 24 meters skid marks on the road while stopping. A police officer observes the near collision and gives you a speeding ticket, claiming that you were exceeding the 35-mile-per-hour speed limit. She estimates the car's mass as 1390 kilograms and the coefficient of kinetic friction, mu-k, between your tires and the street as 0.7. Do you deserve the ticket? Okay, so we can solve this. Maybe I should go back though before I do this problem and just solve the previous problem, right? The with energy conservation. So what we should have done, right, to explain the heating up of the box is define the system differently and then write the energy conservation like this. You have KEI. You have work done by the rope. You have KEF. And then you have delta U internal. All right, so this is what it looks like now. We know that KEI and KEF are the same. Maybe it's 100 joules. We can just subtract 100 joules from each side. These don't even have to be there. This is true too up here. We could just cancel them off and said 0 equals 0. Okay. So what we're left with is what I wanted to point out, that the work done by the rope is expressed as the change in energy between the two, between the carpet and the box, right? That heat that's being given off. And therefore, energy is still conserved and the universe is happy. All right, and we now explain why heat exists after the interaction. Okay, good. All right, now let's try this problem with the person speeding. All right, so with this problem, we're going to do something similar to what we just did a second ago, right? We have conservation of energy, EI equals EF. All right, initial energy, the car is moving, so it's KE. Final energy, the car is stopped, but we have the heat there between the surface. Notice we define the system as being the road plus the car. All right, that is the system. Okay, so because of that, we can then say that we have delta U internal. Potential energy internal. You could also say delta E thermal. All right. we want to know what? Do you deserve the ticket? Okay, so we want to know. We want to know how fast we're going, right? Because I think it was. She estimates that you were exceeding the 35 mile per hour speed limit. Okay, so let's look at this then. So what is our initial velocity? Pretty much, right? Okay. So we have for KE initial, we have 1/2 mvi squared. For delta U internal, we get to use our equation, right? Our equation was delta U internal is equal to force friction kinetic times distance. All right. Good. But we run into a problem. The problem didn't tell us what force friction kinetic is, right? And so we're kind of stuck. So we have to use our long-term memory here to think back to honors physics. There was a formula for force friction kinetic. What was it? Well, it was mu k times Fn. All right. Well, what was our formula for Fn? Force normal is a reactionary force from the surface. So meaning that the car has a downward force on it due to gravity. Just go ahead and draw this in really quick. And it has a reactionary force from the surface that pushes up on the car called force normal. So force normal in this case on a flat surface is just equal to force gravity, right? Okay, so coming back to here, we can then say that Fn is mg. I'm avoiding putting numbers in because maybe there's something cool we can see that cancels off, right? And I think right here we're going to get to see that. Specifically, mass. So that's kind of nice. It saved us the effort of having to plug more numbers in than we needed. All right, so let's get everything over to the right side. Let's just keep with these variables, right? This is kind of fun, not putting numbers in. Multiply both sides by 2. So we're going to end up getting 2 mu k times g times d is equal to vi squared. So if it's vi squared, we'll just square root both sides. And vi is equal to this. Now, was the person speeding? I don't know, right? We got to put numbers in for that. I think mu k was 0.7. No units on mu. G is 9.81. What was the distance? I can't remember. I think it was a 24 meter skid. All right, so we get the calculator out, crunch that baby. That is a lot. I think it ends up being something like this, according to my notes. We didn't exactly do it the same way as I have in my note guide, but that's okay. What we should have got is something like that. And then we can square root that. We end up getting a velocity initial of 18.16 meters per second. All right. This isn't in miles per hour, but you know roughly, if you want to know how to change this, you multiply it by 2 and then add some. Multiply that by 2, you're probably getting, 36 or so. Add some, probably add 8 to that. So 44 miles an hour. So yeah, so definitely speeding. Is it enough to get a ticket? I don't know. I guess it depends, right? Depends where you're going. You're speeding at, right? If you're going five over, I still remember this when I got my driver's license. The I think this was from high school. We had high school like dare class or something. I don't know. There was a officer. His name was Officer Jameson at our high school, and he would talk about how he'd pull people over for going five over if they were going five over downtown. And he said because the downtown in Lapeer, where I grew up, the speed limit was 25. And if you went 30 through the downtown, you were asking for a ticket because people are walking around. There's cars are going slower. Like if you're going 30, that's just crazy through downtown, right? You gotta drive slow through downtown and cruise through downtown. But it's a safety thing, right? So yeah. So anyways, yeah. So ticket is deserved, and that's it. So anyways, that is all. Have a good day and see you next time. All right, bye bye.